Okay, this evening, my cat Ernie has joined us for a discussion of solutions. Hopefully he doesn't look anything too exciting while he does this. Maybe he'll make a solution of his own. Nasty. Anyway, tonight we're going to be talking about characteristics of solutions, sort of how solutions are made, components of them, some basic vocabulary, that kind of stuff that we're going to be using throughout the rest of the chapter. So, moving right along, we got pictures of solutions all over here. Remember, down at the bottom, if you're not a part of the solution, you are a part of the precipitate. It's sad, tragic, really. First of all, what's a solution? Real simple definition in terms of what a solution is. Solution is when one thing is dissolved in another. Pretty straightforward. A little more technical definitions on the screen. A solution is when you've got a homogeneous mixture of a solute dissolved into a solvent. Well, how do you know which one's which? The solvent is usually the one that's present in larger quantities, and the solute is usually present in much less quantities. Or you can say one's dissolved in another, but sometimes if you don't know. So I've got a couple of examples. There's lots of different states of solution, physical states. It could be a solid, it could be a liquid, or it could be a gas. So you've got your typical kind of bottom right there. Sugar dissolved in coffee is a solid dissolved in a liquid to make a solution. Glow sticks, when you make those, there's that little liquid capsule that you snap it, releases some hydrogen peroxide that causes that reaction. It's a liquid dissolved in another liquid. Or top left, if you're taking a look at a soda, it's a gas that's dissolved in a liquid. That's what makes it fizz. You can even talk about air itself. Is some gases dissolved in other gases. So a solution is simply one thing homogeneously mixed throughout another thing. And the key word there is homogeneous. Remember, they're mixed together basically at the molecular level, very, very evenly distributed. It's kind of more challenging to get those components of that mixture separated from one another. So what causes things to go into solution? At the molecular level, the typical solutions we're talking about are things dissolved in water. That's kind of where we're going in this chapter. It's a little bit easier for us to kind of limit our discussions a little bit. But remember, water molecules are polar, and polar again means that they've got charged sides to them. So if you take a look in this diagram over here, you can see those little water molecules with these little red guys with the little white kind of bits on the side. Well, oxygen tends to act negative. The hydrogens tend to act kind of positive. So you can see this chloride ion right here. It's got all the little hydrogens bonded to it. The oxygens are kind of turned away. Sodium's the opposite. You've got a sodium ion up here, and all those big negative oxygen ions are kind of towards it. The hydrogen molecules are sort of turned away. And in this way, each of those little water molecules can act like little positive or negative magnets to kind of pluck the other ions out of their crystalline form. So when you've got, say, a salt solution that's out there, the little water molecules kind of dig their way in, sort of burrow in, so to speak, and kind of pull out the positive ions and pull out the negative ions, sort of draw them into solution, then sort of mix up, either by temperature, by stirring, a variety of other things. Solutions don't always form, though. You guys know that you can make a variety of things where you plop one thing and something else and nothing happens. With ionic compounds, or typical compounds like we're used to dealing with the salts that we've dealt with in chemistry all along, they will form a solution. Ionic salts will form a solution if the attraction between the ions in the salt and the water is greater than the ions to each other. So, for example, those chloride ions are more attracted to the water than they are attracted to the sodium ions, and that's what allows them to get pulled apart. There are cases where that doesn't happen, where you plop a salt in there of some sort and it just sinks right down to the bottom. How many precipitates have we seen, like this big yellow precipitate over here, that for whatever reason, this looks like lead iodide to me, but for whatever reason, this lead and this iodine, when they bond together, they don't want to be separated by water, so they stick together and they literally just fall out of the solution. So again, not everything always forms a precipitate or a solution, and it's just based upon how much attracted they are to each other versus attracted to the molecules in water. That's not the only case. Polar molecules, like water, attract other polar molecules. So when you've got things like sugar, this diagram on the top left is showing sugar molecules dissolving in water. And sugar itself is polar. There's little hydrogen hydroxide groups attached with sugar, and those get attracted to the water molecules, and that helps them pull into solution. So water will attract ionic compounds, the positive negative charge of the ions. Water will also attract the semi-charge-ish areas of polar compounds and pull those in. However, polar compounds cannot pull in non-polar compounds, and this is this oil and water down in the bottom right corner over here. It's kind of like a magnet trying to be attracted to wood, where the water is the magnet and the oil would be like the wood. That you can put them together, but they're really not going to combine the same kind of way. However, and there's this little caveat down at the bottom here, if you've ever used Goo Gone before, there's a variety of other things. Non-polar compounds will dissolve in non-polar solvents. So oils will dissolve other oils. And things like Goo Gone is great for adhesives and oils and things like that because it itself is an oil. It's non-polar, so it can dissolve other things that are non-polar. And that's why it makes it a good Goo Gone kind of solution. So, humorous moment for you. Which one of the following will dissolve in water? We've got a lovely, I hope that's not a male, brown bear over there. We've got a lovely black bear looking for lunch. Baby panda bears. Nice little koala bear sticking his tongue at you. And of course our lovely bear down here at the bottom. Which one will dissolve in water? Ready? Terrible joke, 3, 2, 1. The polar bear, of course. Polar bonds? Anyway, lame. Moving on. So, talking about types of solutions and qualities of solutions. We can describe solutions as being strong or weak, concentrated or dilute. These are terms you know. Concentrated and dilute are, first of all, two terms that you need to understand are relative terms. It's not an absolute value. When you say something's concentrated, you have to say, more concentrated than what. And these refer to the amount of solute versus solvent. So something's concentrated means it has relatively large amounts of solute and relatively less solvent. If it's dilute, it's got lots of solvent and relatively little solute. So you can take a look at the pictures up at the top. I don't know what those actually are, but if that was Kool-Aid, for example, this one that's over here on the right has lots of solvent, lots of water, and relatively little of that, say, Kool-Aid powder. This one over here on the left is definitely concentrated. You can tell even by the color. Relatively little water by comparison, and lots more of that solute is dissolved inside there. The term saturated means that you've dissolved as much of that solute as you possibly can under normal conditions. And if you've ever made Kool-Aid with too much sugar before, you know that there's a possibility to get that stuff just to settle down to the bottom. That's what saturated means. It is possible to make a solution supersaturated, where you dissolve more in it than you normally would. Usually supersaturated means you have to take a compound, a solvent, and heat it up, and then dissolve something in there, and then slowly cool it down. And sometimes you can kind of trick a little bit more solute to stick in there than you normally would otherwise. But supersaturated is not one we're going to see. So concentrated and dilute, important ideas, and the term saturated is another important idea from this. Keep in mind that not everything is as soluble as other things. Some things can dissolve a lot in water, some things can't. This little thing right here is a solubility curve, is the name of this graph. And if you take a look at it closely, you can see there's, 12 or so different compounds that are listed on there. All of them would be classified as salts of some sort, even though only one of them is actual salt, and sodium chloride's right down here, the blue line. But this is how much, the vertical axis, how much grams of that salt can dissolve per 100 grams of water. And this is at temperature. So you can see temperature has a big role in changing solubility. Usually the warmer the water is, the more can dissolve. But if you take a look at each one of them, say for example sodium chloride at 10 degrees, it can hold, 35-ish grams of sodium chloride could be mixed in water. But look at calcium chloride, it's more like 65. Sodium nitrate's more like 80. So it kind of depends on the characteristics of the particular salt. This is not something you'd need to know, like off the top of your head, but I do want you to have that understanding that, number one, the type of salt is going to affect how much of it will dissolve. Solubility is a characteristic of the salt. But then number two, that temperature does have this effect that typically, other than cesium 3 sulfate, bizarre, other than that, pretty much everything gets more soluble as temperature goes up. So there you go. How fast can solutions form? You guys know probably some of this from your just kind of daily thing. If you want to make something dissolve, there's a couple of things that you can do. Number one, and I already mentioned this, temperature. If you want to make something dissolve faster, you heat it up. Sugar dissolves faster in hot water than cold water. Not only can it dissolve faster, but yes, more can also dissolve, but it does dissolve more quickly. And that typically has to do with the fact that there's more energy. Those water molecules are bouncing around faster. They can be pulling the ions, things out pretty quick. Surface area, number two. Surface area has to do with the size of of the grains. So you've got two different pictures here. I'm not sure. I think these are both sugar, if I remember correctly. This top one is like a really rock salt or rock sugar kind of thing. This one on the right's more typical granulated sugar. If you've got really, really small particles, there's more places for that water molecule to attack. If it's a big particle like this, it's going to take a lot longer for that solution to form, just because the water can't get to it as well. So surface area will make something go faster. And then the last one, you know this already too, stirring. The simple fact of bringing more water molecules or solvent molecules into contact, adding a little bit of energy in that way. But it's typically this is sort of the concentration gradients, making sure that as much water as possible is being completely exposed to that particular solvent or solute. Sorry. So temperature, surface area, stirring, three ways that you can change the rate at which a solution would form. So there you go. Basic ideas about solutions. Number one, you need to know parts of a solution. You need to be able to use the term solution, homogeneous versus heterogeneous, solute and solvent. You need to realize that solutions can be any state of matter, solid, liquid, or gas, and probably be able to come up with some different examples of those. You should be able to describe at a molecular level or draw a picture at a molecular level of what solution formation would look like, how those little water molecules would arrange themselves around different ions. You need to understand this phrase, like dissolves like. That's a big one to take with you, that polar solvents like water will dissolve either polar salts or will dissolve polar compounds, I guess, or ionic compounds. That non-polar solvents like oils will only dissolve other non-polar substances. Third, you need to understand what a solubility curve is and that idea of concentration, some of the factors that affect concentration, and then what are the things that can change how fast a solution can form. So there you go. If you're looking for a 4, you can be looking up a question to this lovely answer up here, like super ice. Why is it that salt melts ice? What is it about that process that causes a solution? And then you could also take a look at something called the colligative properties. Colligative properties are properties of solutions, and that has to do with when we dump things in a solution, how does that affect things like freezing and boiling points? So there you go. See you in class tomorrow.